Hello and welcome. This is section 1 of chapter 1 called functions. We're going to split this apart into A, B, and C today. So what is our main goal? Well, our main goals are we're going to write a set into interval notation. We'll learn what that is if you don't remember. I can determine functions from relations. So we're going to look at a relation and determine if it's a function or not. And then we're going to apply the vertical line test to determine if something is a function or not as well. So let's review set builder notation again. I'm going to skip the words, but we're going to look at here. This is the set of all x such that the condition on x can apply. So that is set builder notation, and we've already done this. And a quick example is like for all of x such that x is going to be bigger than 4. Now, this is something very common. We could also add other things in set builder notation. We can also add like x happens to be only integers, which is very nice about set builder notation because then I can skip around and be like, hey, anything bigger than 4, that's an integer, which is like 5, 6, 7, 8, 9, but it's none of the decimals in between. So set builder notation can be very nice. So let's relate that to interval notation again. Again, you can read what this is again, but we already did this. It's where we're using brackets, closed brackets, which will represent these square ones that include or is equal to that endpoint, and parentheses, which is going to be round brackets, which will be that open interval, which does not include. So this is kind of something that we'll be doing when we know that we have everything from one point to another. We can't have any gaps in between, such as like it can't be the integers 4, 6, 8, 10 going on forever. But we could just do the integer 4, 6, and 8, but not forever. So that's one limitation to interval notation. So let's do a quick example again, just as a refresher. So set builder in interval notation, we have the set of all x such that x is between -7 and -5, but it is also including those. So then we're going to have a filled in circle. So from -7 to -5, we close those in and we draw that. Now what does that mean? Well, that means I have a square bracket here and a square bracket here because they are equal to. And I'm going from -7 to -5, and that in fact is my answer of interval notation. It says everything from -7 all the way up to -5. Including the endpoints. This includes -6, -6.11111111, or whatever number in between that is irrational or rational. It's every number in between. Now something slightly different. It's almost identical except that I do not include one of the endpoints. So again, we include the -7, but we have an open circle around -5. So again, how you do that? Well, we do a closed bracket from -7 all the way up to -5, but we have to have an open bracket because we do not include that -5. So this is a nice way of just redrawing that number line. So another example of, again, where we've done this before, so we're going to do the set of all x such that x is greater than 4, which is kind of our starting example. So we go to 4, we have an open circle, and we're everything this way. Now again, how do I do that? My answer is, well, we want a roundy bracket because I do not want to equal 4 because it's not equal. And then I go all the way up to, well, it's going on forever, so you just say it's forever, and we never, ever, ever include forever because this is not a number. It's just the idea of going on and on and on. So this would be my interval notation. So one last example is if x is less than or equal to 3. So if I just say the set of all x such that we're equal to -3 and we're everything below it. So notice how we have to start from the left side and build our way up. So from -infinity, all of these numbers over here, and it goes all the way up and stops at my endpoint of -3. So, and that is inclusive. So again, -infinity or positive infinity have to be roundy brackets. Notice how it goes least to greatest, just like the number line, so it always has to match what a number line is. This is a common mistake. A lot of people will flip this around. So make sure you're checking that you always have the smaller numbers on the left and the larger numbers on the right. So that leads us into talking about functions, because we're going to deal with functions and then write our solutions in either interval or subfielder notation. Just as a refresher, that's why we did that. So we're going to talk about what is a function. Well, a function f from a set A to B is a relation that assigns exactly one element of B to each element of A. So there's something that is very important later. We'll talk about one-to-oneness and onto, and if you remember that cryptic functions, we talked about that already. Something just to highlight is we'll talk about this kind of form a little bit later, and this one is not super important right now, but we will kind of define it a little bit just later, just to note it in the background. So like f is a function from A to B. So it's like saying all these elements A go on to B. This A right here is actually the domain. It's like your inputs of the function. So remember, those are your x values. So domain, we already know this, are my x values. And then my range is the set of actual outputs of the function that could possibly have come out of it, which is going to be my y values in this case. So we'll talk more about the codomain at another point. So let's go ahead and just move on. So let's do a couple identify functions from relations. So we're going to give some relations here and see if it's actually going to be some sort of function. So we're going to look at relation 1, and we have the domain. These are my inputs, r, x, n, and w. So it's looking good so far. I have all separate or different function inputs. Let's see how they go. So I like just drawing some sort of a map. So r goes to x, we have x goes to z, we have n goes to a, and also w goes to the a. So now, is this okay is the question. In fact, to answer that question, this is indeed fine. We can have two different values in the inputs. So if I plug in n or w and it goes to a for both of them, that is totally fine. So this is in fact a function. So we're going to say this is a function. This is totally fine. So you can have the same y values. That's totally fine. Totally okay. As long as our x inputs don't go to more than one value. So for instance, where it's not okay is like you see I have E here. E is going to the letter D. E is also going to the letter N. So if I plug in an input of E, what answer should I get? Well, I don't know. I'm either getting D or N. So that is something that is not okay. That is not a function because E goes to two different values, and that is something that's not okay in a function. And we're going to show this as a demonstration with a vertical line test, if you've ever heard of that before. So continuing that, just two more relations here, just checking it out. I like to again draw arrows. So n goes to a door, E goes to a leaf, Y goes to a leaf, and A goes to a leaf. A big giveaway, these are all different, so that is kind of a good check mark in my mind. The Y values can have multiple different answers. And just think about this graphically. So if this were numbers, you can have a function that kind of looks like this, and then it goes down, it goes back up, and down, and back up, and it goes this way, where it touches this point here, and here, and here, 3 different times. So the y values hit 3 times. This is a function. It will pass something called a vertical line test. It just won't be a specific one-to-one function, which was what we'll talk about sometime. So this is, in fact, a function. Now, let's look at the next one. We're going to match things. So look, b goes to 4. Wait, b goes to 2. No, b goes to 3. Which one does it go to? So if I plug in b, I'm going to either get 4, 2, or 3. It's kind of a guess. Which one does it work? So this is not a function because it's not okay to plug in something. And we want one answer coming out if I plug something in, because otherwise it's chaos.